Okay, here we are, folks. Welcome to the Humanist meeting for January 2024. And tonight we have our friend and colleague, Dr. Holger Meyer, who will explain the meaning of life and all those things to you. Or the creation of the universe, whatever. Really, you all know Holger, so it's hard to introduce someone so well known. But actually, we do have in this organization some really amazingly brilliant people, and Holger is one of them. And so I'm sure you all will enjoy his talk as much as I'm sure I will myself. So, Holger.
Thank you. All right, can you all hear me? Okay, and on Zoom as well, can somebody give me a thumbs up? I think it works all right. All right, let me actually screen share so people on Zoom can see the slides well. And start presenting. Too many things. Hold on. All right. Yeah, so the idea here is that really our understanding of the universe has advanced significantly in, certainly in the last 100 years, but also in just the last 10 years, actually. And so I guess I really just want to bring all of you up to speed if you haven't followed the science literature. So, if you went to school, 50 years ago, not that that would apply to anybody here, much of this hasn't been discovered yet. And if you went to school 15 years ago, then probably you still had textbooks that didn't cover some of this. And so anyway, hopefully it's going to be interesting, and please interrupt me and ask questions and so on. All right. So this is just the blurb that I sent out that you may have read. And so I have three parts. I want to talk in the first part about the Big Bang model and how it came about. And so this is the part that's really, we are just really very confident about that. There's pretty much no ambiguity, and I'll explain how we have really two totally complementary ways of knowing this. And if you claim some extraordinary thing and you can prove it one way, it's still a little bit suspicious because, maybe there's still some loopholes somehow. But if you have two totally complementary, independent ways of confirming it experimentally, that's really pretty solid evidence. Then after that, and going back to about 300,000 years after the Big Bang, since then, we really kind of know what happened. Beyond that, what happened in the very early universe, much closer to the Big Bang. And so I'll talk a little bit about inflation, cosmic inflation, and baryon acoustic oscillations. And that's really the new stuff. So if part one sounds like I heard about this before, you probably may not have heard about you probably may not have heard about cosmic inflation and baryon acoustic oscillations in as much detail. This is still pretty solid. I really think we have enough evidence. I would be surprised if it turns out that there's a different model that's more accurate and doesn't somehow just build on top of this. And then in part three, finally, what really, how did this really start? Why was there a Big Bang to begin with? And that's really something we probably aren't ever going to truly know. It's just not really experimentally accessible. But I think we can make reasonable speculations based on our understanding of physics and have some reasonable speculations that may or may not be true, but it sounds good anyway. So, so that's the rough outline. So before about 100 years ago, really the assumption was that the universe must be static. Now, static doesn't mean that the Earth doesn't orbit the Sun and that the Sun doesn't orbit the center of the Milky Way galaxy, but it means on a long time scale, you know, there are as many stars and galaxies now as there were 100 billion years ago and as there will be 100 billion years from now, right? The universe is kind of always there, and also, you know, on a quote-unquote small scale, things move and things change, maybe even planets or stars evolve, but the universe must be static in some sense, surely. It was just kind of the simplest assumption as long as there wasn't any contradictory evidence, right? It kind of makes sense to start with the simplest assumption if you don't have any need for a more complicated model. But beyond that, it was also just the bias, you know, it just seemed the most logical assumption, and so really nobody questioned it, right? But even in 1823, actually, there was some indication, really, if you thought it through carefully, that the universe was not infinite and in space and has existed for an infinite time. Because as Olbers first observed, the sky is dark at night, and that wouldn't be the case in an infinite universe that has existed infinitely long. Who has heard about Olbers' paradox before? Not really? Okay, so if the universe is static in this sense and has existed forever and is infinitely large without any boundaries, then think about it. You look in some random direction and sooner or later you will hit a star, right? And so if the universe really was infinitely old because it always existed and is infinitely large because it, you know, just shouldn't have any boundaries, well, then actually there should be radiation from some, no matter how distant star, reaching us from every spot in the night sky. And so Olbers was saying, well, there must be something wrong with the static universe. One of the assumptions must be wrong. Either the universe isn't infinitely old, or it is not infinite, or it's doing something else. But nonetheless, most people believed in the static universe. It was just like in Newtonian physics, in classical physics, the way we start teaching in Physics 1, space and time are just given, right? We don't question that. We just have three perpendicular directions of space, and time is just what I see on the clock ticking away, right? But it may not be quite so simple. And so, but the static universe was the prevailing attitude until Albert Einstein came up with general relativity. He came up with special relativity in 1905 and then expanded on that idea with general relativity in the following decade or more. And although Einstein himself was a theoretical physicist, the need for changing classical physics was really brought about by an experimental observation. So in the 1800s, James Clerk Maxwell came up with a theory of electromagnetism, and that showed that light was an electromagnetic wave, and light must be traveling in some medium was the prevailing idea. If it is a wave, a sound wave travels in air, a water surface wave travels on the surface of water, there must be some medium that people speculated was the ether, because they didn't know what to call it, they called it the ether. And then Michelson and Morley tried to find evidence for this hypothetical ether, and instead their experiment showed that the speed of light is just constant for every observer. And so that's not something Einstein postulated, that was something that was really experimentally observed. So physics is an experimental science, and even these somewhat fantastic claims, until you get used to it, really are founded in experiment. So, so the consequence then is that we need to change from classical relativity, where of course, even in classical physics, we can have different frames of reference, right? If I'm walking, whatever I'm holding in my hand seems to be at rest to myself, but it seems to be moving from your point of view, right? So even in classical physics, we can transform back and forth between different reference frames. But in general relativity, especially in general relativity, things get more complicated, and the fact that the speed of light is constant causes really time to be relative. And then if you want to incorporate gravity into this new model, you need to expand special relativity into general relativity. And in general relativity, space is now curved. Space is not just everywhere three perpendicular directions that are constant and throughout and permanent, but space is influenced by matter, and in turn, matter influences space. And so that was succinctly summarized as matter tells space-time how to curve, and curved space-time tells matter how to move. That is kind of the one-sentence summary of general relativity. But you see, you know, if you have a planet, it deforms space-time. This, of course, shows only 2 of the 3 spatial dimensions, but you get the idea. And now a planet, or even a particle of light, it thinks it's going straight, but it really, from our point of view, changes direction, because what seems locally straight really is a curved trajectory in this curved space-time. That's kind of the idea. And so the upshot of it is things really do get vastly more complicated compared to this now obsolete picture that space is just there and is permanent and is 3 directions, and that's all there is to it. And so then, of course, after realizing that we need to modify our understanding of space and time, the question then is, what is the implication of this for how the universe looks like? And so Einstein himself, and later many others, tried to derive what this means for the universe on a large scale. And Einstein realized that general relativity really isn't compatible with a static universe the way people envisioned it before. And so, although there were hints, I mentioned Orbert's paradox, but there were other indications. But now with general relativity, really the universe wasn't static unless you were so convinced that it was, you added some fudge factor into your equations. And so if you've ever heard about the cosmological constant, that's how Einstein fixed the situation to allow for a static universe. And then later on, Lemaitre and Hubble and others showed that the universe is actually expanding. And so Einstein said, well, darn it, that was my biggest foolishness. And the word he used was Eselei, which is like, you know, act like a donkey. And so just looking ahead, so, and as a side note, later we discovered cosmic inflation, which in Einstein's field equations actually just looks like a term that is like the cosmological constant. And so then people were quipping, even Einstein's biggest mistake was still pretty brilliant, although he didn't know at the time. But anyway, so, all right, so there were many observations by looking into the sky, but really the urgent need to update our cosmological model initially came about by having general relativity as a new theory as well. And so, all right, so now we throw overboard the notion of a static universe. So what's going to replace it? And so pretty soon, people came up with the idea of the Big Bang. And so I think I skipped over this picture. There was a Belgian mathematician, astronomer, and Jesuit monk, George Edward Lemaitre. This picture was taken in about 1930. And he actually came up with the concept that the universe is expanding, but he published in a small French journal that didn't have large circulation outside the Francophone world. And so Hubble didn't know about it, and a couple of years later published a paper that was more widely read. And so we credit often Hubble with first coming up with the idea of a Big Bang, but actually really it goes back a few years more to Lemaitre. So how do we know this? All right, we look at the universe and we can see all kinds of stars and so on. Now, we can't go out there and take a stopwatch and see how fast they move. So how do we know if they move away from us or toward us or whatever? Well, you all know the Doppler effect for sound waves. When a car is going past, you hear it as, right? It's high-pitched as it's approaching you, and then lower-pitched as it moves away from you. And the reason is that, you know, the next sound wave peak is emitted as the car is already closer, and so the peaks kind of get squished as the car is moving toward you, causing a shorter wavelength corresponding to a higher frequency, a higher pitch. And then when it's moving away, there's one wave peak emitted, and before the next wave peak is emitted, the car has already moved further away from you, and so the waves are more stretched out, corresponding to a lower pitch. The driver inside the car, of course, doesn't hear the driver inside the car hears a constant pitch, right? So the Doppler effect for light is because light doesn't really move in a medium like sound waves do, but the moving source still has a different relativistic reference frame, and so due to time dilation, there's also a relativistic Doppler effect for light, and it works the same way. So instead of pitch, higher pitch and lower pitch for sound waves, the different frequencies of light correspond to the spectrum of colors, the spectrum of the rainbow, right? And so instead of something approaching us being higher pitched, if a light source is moving toward us, we would see it shifted into the blue towards the UV end of the spectrum of colors. But if it's moving away from us, then it would be red shifted towards the infrared, towards the longer wavelengths of the light waves, all right? And so most objects in the sky kind of look white to us, right? If we look at a star, it really looks white, like it has all kinds of wavelengths in there. But really there are certain elements that have specific frequencies or wavelengths of light they emit. When you look at those old sodium street lamps, they are yellow, right? Because sodium has an atomic energy transition that corresponds to that yellow wavelengths. And so every element has kind of its own fingerprint of spectral wavelengths. And so we know what that looks like when we measure those wavelengths here on Earth. And we can see, if we look at stars, those same peaks in the spectrum at the certain wavelengths, but they are shifted just a bit towards the red. And so, as fantastic as it may seem if you've never thought it through, although those stars are thousands of light years or more away, we can still tell if they are moving toward us or if they are moving away, all right? By using the Doppler effect. And then the second piece of information, we want to know how far away is something. And for some objects, that is actually very difficult to discover, right? If you look into some of the constellations, we talk about them as if all those stars are close to each other because they are close in angle in some region in the sky. But really, oftentimes, one is much closer to us than the other part of that same constellation. That's a star that's much further away, right? So how can we tell how far away or close to us something is? Again, for some objects, it's very difficult, but there are certain objects that we call standard candles. And if we know for some reason how bright an object should appear, then by comparing how bright it actually looks to us through the telescope, we basically know how far away it is. It's like the headlights of a car on the highway. When the car is still far away as it's coming toward you, it doesn't blind you yet. The headlights are not so bright yet, right? But as it gets closer and closer, it appears brighter, right? It's the inverse square law with distance, right? So the further away, the dimmer it appears. Although, of course, the light output of those headlights of the other car doesn't truly change, right? It's always the same brightness. The light bulb emits always the same amount of light. It just seems dimmer when it's further away. And so if we know how bright that headlight or star actually is, and how bright it appears, we can also measure distance. Now there are different types of objects for which we can model what the physical process in that star or that object is, the Cepheids and other things, but one particular one is also type 1a supernovae. Some stars, depending on their mass, as the star evolves at the end of its life, some stars become supernovae, and this effect of undergoing the supernova explosion, even if the star started with a different mass from another one, they shed mass until they compact to the size where they become a supernova. And so we can model, we can understand the process that leads to a supernova. And no matter how much mass the star initially had, it has always the constant mass when the supernova process happens. And it always is the same brightness supernova within a few percent anyway, for different stars doing this supernova process. And so we can use that fact to know how bright that explosion was. And we can also then observe how bright it appears. And so we have distance measurements, and then from the frequency shift, from the Doppler effect, we have velocity measurement. And so what would you expect? What should that plot look like? I mean, I've shown the answer, so it's not a difficult question, but if I hadn't shown the answer, what would you expect? You would probably say, oh, there are some stars out there that are moving toward us, and there are some that are randomly moving away from us, right? It should be all over the place, right? Instead of falling along a line like this, you probably would assume that it should be just a cloud of points that filled the entire plot, right? That would be probably true in a static universe, right? However, it falls along this line, and so what it's saying is, if a star is further away from us already, then it's also moving away from us at a faster speed. Now, obviously, there are small variations to this if we look at our own Milky Way galaxy. If we look toward galactic center point, the stars on one side are moving more toward us, and the stars on the other side are moving more away from us as the galaxy spins, right? But the motion of stars in galaxies is actually relatively slow compared to the speeds you get after you go a reasonable distance away. And so this, of course, there is that small motion of objects due to gravity and so on, but the bigger dominating effect is that the further away, the faster they move away from us. Okay, so what does that mean? Does that mean we are at the center of the universe if everything's moving away from us? That would be quite a coincidence, right? No, it doesn't mean that. Think about, a dough with raisins in it, and now the dough rises, and any two raisins you can think of are moving away from each other, right? As the whole thing is stretched in every direction, right? So it doesn't mean we are at the center or anything. If you did this observation from any other solar system or, exoplanet around another star, you would see the same thing as well. Okay, so we observe this thing, and imagine being the first person to make this graph. That would be a shudder down your back, right? Like totally mind-blowing. All right, so what does this mean? If everything's moving away from us, if the dough is rising, expanding, well, you kind of play the movie backward. Everything must have shrunk in the past, right? Everything must have been smaller, and hence a Big Bang, right? Seems reasonable, right? So far, you might argue with this picture. You might say, well, seems like it's all expanding right now, but what if it was all just in a really small space, but not a single bang, right? Or you could quibble with this. The observation is what the observation is, but I think by this point, you might still say, yeah, definitely compatible with the idea of a Big Bang, but I'm not 100% convinced, right? Extraordinary ideas need extraordinary proof, right? Well, okay. What happens if you compress something into a smaller space? If you compress a gas, the universe largely is just filled with gas, right? If I look around here, that's not true, right? Solid objects, but most of the universe, stars and so on, and intergalactic space is just filled with plasma in the stars and, some atoms everywhere in the universe. So anyway, You compress it, what's going to happen? Well, it was compressed. Why did it explode? It must have been really hot, right? If you take a spray can and you let the gas escape from the spray can, the nozzle gets cold, right? You know that, right? That's because the gas is compressed inside and now it can expand, and as it expands, it cools down. If you did the opposite, if you compressed it back into the can, that would heat it up, right? Okay, so now the universe is at a comfortable temperature here on Earth. The sun, of course, is a bit hotter, but anyway, so the universe isn't crazy hot today, right? But at some point in the past, if it was smaller and smaller and smaller, it must have been hotter and hotter and hotter as well. And so right now you can see me and I can see you because particles of light can pass through the air. Particles of light can pass through the air because the air consists of neutral atoms. Atoms have as many protons as electrons, and molecules formed from atoms still have as many protons in their nuclei of the atoms and electrons combined in the shells. So photons don't interact with neutral atoms, not as much anyway. But if everything gets really heated up, eventually there aren't any atoms. The electrons, you heat something up and it just vibrates more, and eventually the atoms tear away from the nuclei, and everything is ions and electrons. Instead of neutral atoms, when it becomes hot, you have charged particles. If it was daytime and I looked towards the sun, the photons of the particles of light reaching my eye from the sun, anybody know how long that takes?
8 minutes.
Couple of minutes, right? 8 minutes. So the sunlight hitting us was emitted from the surface of the sun 8 minutes ago, right? But the energy carried by those photons is from fusion reactions deep inside the sun, right? And the sun is actually made out of a charged plasma of charged particles. The sun is hot, and it's not made of neutral particles, it's made of a plasma. And so the fusion reaction that happened to release the energy deep inside of the sun, that may have happened 10,000 to 100,000 years ago, and then that poor photon bounced around and got absorbed and re-emitted and just was trapped inside the sun until it randomly, through a random walk, reached the surface, and then 8 minutes later it got to Earth, right? So if the universe is not filled with neutral atoms, but is filled with a hot plasma, like a star in the current universe, then the universe is not transparent to radiation, okay? So what should we expect? We should expect that there were no photons that could travel long distance, and when the universe cooled down to about 3000 Kelvin, half the temperature of the sun approximately, that's when that thermal energy was low enough so neutral atoms could form, and then the universe became transparent for light. Okay, so then light could travel through the universe. Okay, so we know at what temperature that happened, and so we know that the photons that traveled at that time, which I can't tell you why yet, but it happened about 380,000 years after the Big Bang or so, the universe cooled down enough to become transparent. Okay, and it was about 3000 Kelvin hot at the time. And then it cooled down further as it expanded more. And we can tell how much more it expanded based on the knowledge from Hubble Hubble's measurements. And so as the universe expanded, that radiation would have been stretched with the space stretching, right, with the universe expanding. And so instead of being short wavelengths radiation corresponding to the high temperature universe, that short wavelengths would have been stretched to what we call microwaves, a few centimeters in length, in wavelengths. And so the second piece of evidence, Arno Panzias and Robert Wilson stumbled across it by accident in 1964, okay? They were trying to measure microwaves from the sky to just see if there were maybe sources, or also to transmit among the ground, to just study microwaves. And they just had this noise. And so they just wanted to know what's going on. And, you know, they point their antenna in a different way. This was like a sheet metal construction horn antenna. And so they just pointed it to a different part in the sky, and they still had that noise. And so they looked at the electronic amplifiers, and they suspected that it was pigeon droppings inside the antenna, and they scrubbed it clean, and they just couldn't get rid of this noise. And so eventually they realized it wasn't really instrument noise or some experimental mistake. They realized it really was radiation coming from everywhere, and soon they were contacted by theoretical physicists saying, hey, that radiation you discovered, that's actually what we nowadays call the cosmic microwave background, and it is that radiation that started to transmit through the universe from all directions at that time when the universe became transparent to radiation. And so it's a completely different measurement from measuring how fast stars and galaxies move and how they are redshifted or whatever, right? It's totally different. It's looking at this microwave radiation hitting us from every direction. And that's the afterglow of the Big Bang, is sometimes how people refer to it, okay? And the thing is, not just is it there, but also the temperature that we see this radiation at now, just above 2 degrees Kelvin, very, very cold in the universe today. Well, we know based on Hubble how much that should have been compressed, and we get exactly the temperature where atoms dissociate into plasma. And so these, it's not just qualitatively these two things agree, but quantitatively they point to the same underlying mechanism, namely the expansion of the universe, at least from that time when it was compressed enough to be a plasma. Okay, so we have since then sent satellites into space to study this in a lot more detail. There were 3 NASA and ESA, North American Space Agency and European Space Agency. First was the Cosmic Background Explorer, COBE, and then with a better instrument and more capabilities, COBE had established that the temperature was almost exactly the same everywhere, but there were tiny anisotropies, tiny changes in temperatures. And so the microwave anisotropy probe MAP, that was later renamed to honor Wilson into the Wilson's microwave anisotropy probe, probed this further. And then the Planck satellite refined it even more. And so what's shown here is a picture of the sky. So, you know, if you look at a world map, it's kind of a projection of the sphere of the globe. and it looks kind of that shape, but you look down everywhere. But if instead of looking down at every point you looked up into the sky, you could still project it onto a similar kind of map. So there's the equator and so on, but this is the map showing if you look up from every point on Earth, right, in every direction into the universe. And what's shown here is very exaggerated. What we see is really the same temperature everywhere to the first decimal places, and then only tiny variations in that temperature depending on exactly where you look. And so those tiny variations are shown here. There's regions in the nights in the sky where the cosmic background radiation is a little bit cooler, and some areas where it's a little bit hotter and so on. But really those are tiny, tiny variations on a pretty darn uniform background, because for those of you who know what a black body radiation is, it's really black body radiation with that cold temperature that the microwave background has stretched out to. But those tiny variations are becoming important in a moment. But anyway, so that's, I've said everything that's on this slide pretty much. But so again, just really quickly, we have now the observation of stars' brightness and redshift, and that points to a Big Bang. And we have the observation of the cosmic microwave background, and that on its own, you know, you might say, well, there's radiation hitting us from everywhere. How does that point to a Big Bang? But I challenge you to find the source of that radiation without a Big Bang. What is your model that explains the cosmic microwave background? Well, the Big Bang does it, and does it so that the numbers come out the same as with the Hubble expansion. And so I think that's really pretty conclusive. Any alternative theory that you want to propose would need to also explain the Hubble constant, or that observation of more distant stars appear to us more redshifted, and would need to explain the cosmic microwave background we observe, and would need to have some other advantage over the current Big Bang model. So nobody has come up with anything, and I don't think anybody ever will. So we are really pretty confident that for about 13 billion years, the universe has been expanding, and 13 billion years ago, it was very much smaller than it is now. But at that time, when it became transparent, it was not a point yet, right? That would have been another 300,000 years before, just going with that constant rate of the Hubble expansion. So with these observations, we can look back to a time when the universe was, we think, about 380,000 years old. That's pretty darn good, right? Much better than we can do in most other ways of thinking about this, but it's not all the way back to the Big Bang. But this part of the story, I think, is really pretty damn solid. But before I go on, any questions? Yeah, Corey?
What or where is the universe expanding into?
What or where is the universe expanding into? Well, not into anything. There isn't something outside the universe. If you have a rubber band and you just pull both ends, the rubber band is becoming longer without, it seems like new rubber is forming in between, right? Really, it just becomes thinner. But okay, so with stretching the rubber band, you are moving into existing space. But if yeah, it's hard to come up with an analogy that really makes sense. Think about a kid's party balloon you inflated. Well, the surface of the balloon is small, and then as you blow more air in, as it inflates, the total surface becomes larger, right? You have more real estate on the surface of that balloon. It's an imperfect model because it's really just a two-dimensional thing expanding the surface of the balloon, expanding in a pre-existing three-dimensional space. So it's maybe not helping you to really understand what you want to understand. But the point is there isn't like an edge to the balloon, and it's, you expand it at the edge. It's just the whole thing is expanding, right? And so the universe, what if anything is the edge of the universe? Well, could we go there? What would happen if we keep walking in some direction? What would happen? Remember the question about the now space is curved, right? We said space is curved in general relativity. Well, the universe on a large scale could have different shapes. It could either be flat on average, or it could be kind of concave or convex. It could have positive or negative curvature. And so if it's got curvature one way, it could be that you just kind of come go around and come back eventually. If it had the other curvature, you would just never reach an end. It would be infinite. And so it would still stretch, but it's already infinite. And so the question, what does it expand into, wouldn't present itself, right? It's already infinite in that scenario. How does that influence the idea that there might be parallel universes? I'm going to get to some version of a multiverse. All right. Yeah.
You speak very casually, as well as other scientists, and I guess we do too. We talk about the 380,000 years.
Olger, can you repeat the questions for the Zoom viewers?
Yes.
Where they make and so on, was 365 days. He said, we talk about these years so casually.
So how do we know those numbers? I mentioned the number, and I promised you that I wouldn't go into a lot of math. So to some degree, you have to take my word for it. But I showed you this graph with the Hubble expansion, right? And so we know this rate of about 70 kilometers per second per megaparsec, megaparsec being a large distance that we use for describing the universe. And so if I have this constant, then I can kind of run the movie backward, right? And as it gets smaller, it gets hotter. And doing that at an age of the universe of about 380,000 years, that's where it would be hot enough so that it's not transparent anymore. So that's conceptually where that number comes from. To go into more detail, I would really need to, take out a pencil and paper, which I'm willing to do later, but maybe not just right now. All right. Lloyd will solve it on the way home himself. All right. So let's see. Any other questions?
Can you hear me?
Yes, we have a question on Zoom.
Yeah, okay. You started out by saying that the universe is expanding, and you finished also, everything in the middle was fascinating, but you also finished at the end saying it's still expanding. Well, if that were the case, everything in the universe would be expanding, including all the planets, right? So if they're expanding, yeah, okay, go ahead.
Okay, right. So if everything is expanding, wouldn't the planets also expand? And with the planets, all the metasticks. And if I use a metastick to measure how long something is, how can I figure out that it expanded if my metastick expanded with the universe? Well, the thing is that space expands, but the atomic interactions between, the electromagnetic interactions between the electrons in adjacent atoms that form the molecules that make the substance that your metastick is made of, or that the planet is made of, and so on, the strength of those interactions doesn't change, and the equilibrium distance between atoms doesn't change. And so as the space is very gently expanding at this rate that seems fantastic, 70 kilometers per second is a huge number, but that's per megaparsec. And so it's really still a very slow rate at which space is appearing or at which things are stretching. And so any molecular bonds or anything around us has time to readjust to the old equilibrium lengths, and so the universe space expands, but a solid metastick or the planet or even the orbits of the sun, Earth around the sun, that does not expand. Does that help?
You mean the sun doesn't expand, but all the planets do?
No, the size of the solar system stays the same because the gravitational strength that holds the planets to the sun, that's given by the distance between, and as the distance increases due to the space expanding, the orbit then contracts a little bit to the old value because the strength of the gravitation is what it was without the expansion. I'm not sure I'm explaining that well. But the upshot of it is space expands, but stuff that's influenced by forces such as gravity on a nearby scale or electromagnetic interactions, that readjusts itself to not go along with that expansion. All right, so yeah, but that's an important question to ask. And of course, if it was true that everything stretched at a uniform rate, then we couldn't even tell. You are right. But because space expands so slowly that electromagnetic interactions have time to readjust the distance between two atoms in in my body doesn't change as the space expands. So they stay the same distance, and so we can measure that space expands because our rulers stay the old lengths.
Okay, you get, that's a good explanation. I mean, you have the knowledge, but my little brain just can't even comprehend it. I gotta get interested in this stuff. I gotta look this stuff up. But hey, it's good. It's good.
I don't know if you can hear him, but he said I need to look some of this stuff up, and that was exactly what I wanted to accomplish with this evening, of course. So,
you're
all right.
Plenty to think about.
All right. Okay, so once more, any more questions on part one? So again, I really think this is the very solid part, and I really hope that this makes sense to all of you at least somewhat, and maybe you need to watch the recording 5 times, but hopefully eventually. And anyway, no, this is really fascinating stuff, but I mean, even if you don't appreciate every detail, or there's a lot of things that are making your head spin right now, the summary again is that we really have 2 totally different ways to determine this, and they come up with exactly the same answer. So there's really, you know, it would be really, really extraordinary if it turns out this is all bogus after all. I mean, I can't see how. So really this is just as certain as you can be certain about anything. I mean, you can always say we are just, you know, Boltzmann brains floating in some alien's nourishing solution and the universe doesn't even exist. But short of that, you know, if you believe that science is at all a worthwhile endeavor, then you can hardly avoid believing in the Big Bang to this degree at least. So, all right. So we already talked about the curvature of space-time a little bit when you asked how does the universe expand or what does it expand into, and I said, well, it really doesn't expand into anything, but the details depend. But all right, so what else does the cosmic microwave background tell us? If we so far, I've made use of the fact that it exists, right? But somehow measuring these tiny anisotropies was important enough so that we built a very expensive satellite, WMAP, to examine it. And then we said, hey, this is still not good enough. We need the Planck mission, which was even better and cost even more money. And we examined it in even more detail. So why go into that much detail? What else is there to learn with the Big Bang? And so there's many questions that are left now, right? We want to know what is the shape of the universe. And by shape on a large scale, I mean, again, so now we understand that space can curve, and it can curve in such a way, you know, that like a planet is held in orbit around the sun, but on a much larger scale. Well, does the universe more look like the top shape, where the sum of angles in a triangle is larger than 180 degrees? Right? If you imagine a sphere and you draw lines from the North Pole to the equator through London, and you go 90 degrees around and you draw a line from the North Pole through Kansas to the equator, and you go along the equator, then each of those angles in your triangle are 90 degrees. And the sum of them is 270 degrees, although we learned in high school that the sum of angles in a triangle is 180 degrees, right? Well, in high school, we dealt with the lower picture there, where it's flat, and in that triangle, the sum of angles is 180 degrees. And if you have some saddle-shaped geometry like the middle picture, then the sum of all angles is less than 180 degrees. And so maybe we can't easily wrap our heads around what this truly looks like for space, because I can only turn around in space and not kind of step out of the universe and look down on it. But I can, in some way, do experiments that let me measure the sum of angles in a triangle. I can triangulate different stars, distant stars and systems, and it seems like I could measure only two angles, like pointing toward two distant objects and not the third angle. But anyway, we found clever ways to actually measure this shape of the universe, and it turns out it's very, very nearly flat. Okay, I mean, it's flat within experimental uncertainty. It's either totally flat or very, very, very close to flat. And maybe you are now saying, that's what I always knew when Newton was still the fashion of the day, right? But with general relativity, there's really no reason for that. The universe could have positive or negative curvature, and there's really really any number should be as likely as any other number. So how come it's exactly flat when there's infinitely many possibilities for it to be curved this way, infinitely many possibilities for it to be curved that way, right? A little bit more or a little bit less so, right? Infinitely many, but only exactly one possibility for it to look like this. Well, those are bad odds, right? If you are a gambler, you wouldn't bet on it. And yet this is the outcome. It turns out experimentally we do live in a flat universe. And another question is, what's the future of the universe hold? Well, we now established that there was a Big Bang. So something pushed everything apart. Now, what's going to happen if I take something and I toss it upward? What's going to happen? If I toss it, it's certainly going to come back down, right? But what if it's a rocket? I could shoot it up with escape velocity so fast so that it just keeps going, and also gravity slows it down. It never slows down to zero and turn around. It just keeps going and escapes to infinity, okay? If I just toss it hard enough, right? And then there's kind of the border case in between where it kind of escapes but asymptotically slows to zero at infinite distance away, right? But so experimentally, well, there was a Big Bang, but how much matter is there in the universe? How much gravity is slowing it down to make it, maybe turn around and end up in a big crunch? Or does it was the bang so massive that it will keep expanding forever? That's another question. If you heard about the Big Bang, but you haven't kept up recently, that was something that was discussed at scientific conferences in my lifetime, right? So, well, which one is it? It turns out about 10 years ago, we found that not just will it keep expanding, but the rate of expansion is actually speeding up. So imagine me chucking that stone up, and maybe there was a period of time where it slows down, and then it's like a second stage booster kicks in and it makes it go faster suddenly. Gravity is still pulling it back, but somehow it still accelerates faster. That's apparently what's happening with the universe. And so there were two different groups that observed in great care this, how fast does stuff move away, depending on how long ago it happened. And so we have evidence that counter to any intuition you should have, that expansion is actually speeding up. And so that was completely unexpected and resulted, of course, in the Nobel Prize for the experimental groups. And so that's something we call the effect of dark energy. We don't know what it is, so we give it a name so we can at least talk about it, but we really don't know what it is. So, but we do have an experimental observation. The universe isn't going to collapse back into a point, it's going to keep expanding. And in fact, the way it looks right now, that expansion is going to get faster and faster again. So, all right, I've answered these questions, but how do we possibly know that? So, experimentally, I told you, but why would it be like that? How is that really compatible with the Big Bang model? And what else does this anisotropy tell us? So it turns out in the very, very early universe, there was, right after the Big Bang, at like 10 to the minus 33 seconds after the Big Bang, basically no time at all after the Big Bang, there was a very short period of time during which the size of the universe just expanded unbelievably. I could throw out numbers, but I won't even bother. It's just mind-blowingly fast, okay? So, does somebody online have a question? Maybe not. I thought I heard something. All right. So we think that there was this period of inflation in the very, very early universe. And if it's so, then it solves this flatness problem, you know, the one versus infinitely many possibilities versus infinitely many possibilities, because no matter what curvature you start with, if you blow it up so that you see only a couple of, you know, only a small amount of it, then it's kind of like the flat earthers, right? The earth looks pretty flat from where I stand here, right? We know it isn't, we know it's curved, right? But it's like the ant crawling on an apple. The apple looks round to me, but the ant crawling on its surface looks around and says, this apple is flat, right? And so you just stretch whatever curvature you start with, you stretch it enough and it becomes locally flat, okay? So, okay, that's nice. It also, there's another thing that I haven't mentioned, but this thermal radiation as the universe cooled down, you would actually expect a little bit more of a variation in it. I mean, the neutral atoms form at a fixed given temperature, and so it should be pretty uniform, but there should still be kind of random tiny variations. And so the fact that the temperature of the microwave background very nearly is the same in all directions, it's hard to understand that it's so close to uniform, because if I look in this direction and that radiation comes to us from 13 billion years ago, so from more than 13 billion light years away, because the source has moved away from us, and I look in the other direction, and that was more than 13 billion years ago, but the universe is only 13 billion years old, so how can those 2 points have been in contact with each other to know that they should be at the same temperature? Well, if there was this very, very rapid inflation, then at one time, very early on, they would have been in causal contact. And so this isotropy problem also is solved by inflation. Now, that's not how we should trust any theory, right? It's just because we want it to be true, because it solves some problems for us. That's not really how it works. But it turns out we have actually good evidence for it. There's a signature of cosmic inflation in the cosmic microwave background, and that's called baryon acoustic oscillations. And so let's quickly look back at this picture. We see teeny tiny variations in temperature in different directions. And so now if I take a random point on this graph and ask 10 degrees over in the sky, is that temperature correlated to the temperature at this point? And what if I take 10 degrees but the other way? And what if I take 10 degrees this way? And what if I take this point and I go 10 degrees over? And what if I take this, right? Any 2 points, but I always ask 10 degrees, I go 10 degrees over, okay? Or I go 20 degrees, right? 1 diameter of the moon, or 2 diameters of the moon, or 3 or 10 diameters of the moon, right? And I just ask, is there any correlation? You can't do this with your eye, right? There's really too many points to compare, and you aren't going to find patterns by just looking at this picture. But if you do it with a computer, you are going to find that there are correlations at certain angular scales, and less correlation at other angular scales. And so instead of angle, physicists and mathematicians use something called a multipole. And so these points here on the left correspond to large angular separations. Like look at a point and look at the point in the opposite direction on the other side of the Earth looking into the night sky, right? Or look at a point and look at a point 90 degrees away, right? Things like that. And then for the higher numbers, it corresponds to points that are smaller and smaller and smaller, closer to each other, okay? All right, so we think that there was this period of cosmic inflation, and there was radiation, and there was more radiation emitted where, due to random initial quantum fluctuations, there was a higher density. Okay, more density, more matter, more stuff that emits radiation and reabsorbs radiation too, but emits radiation. Well, that radiation is going to push stuff apart, right? Because radiation has a radiation pressure. Even light can push stuff. Maybe you've heard about the idea of using solar sails to accelerate satellites over long distances. So areas that were more dense initially would have expanded, sending a shock wave out from those regions. But the matter expanding would have been just the baryonic matter, you and me, stuff that interacts with light when it's heated up to where it's charged particles. We also have dark matter in the universe, which I haven't yet talked about, but it's part of this model. And the dark matter stays behind and pulls all the baryonic matter that we can see back in. And so you end up with this effect of stuff being pushed out by radiation and being pulled back by dark matter, essentially. And so if that happened very early on, then the wave emitted by that could have traveled a long distance, causing correlations in very distant parts of the sky. This first peak here, and then gravity of dark matter pulled it back together and made it expand again. And the second baryonic oscillation is causing the correlation at this angular scale. And then there was a third peak and maybe a fourth, and then the universe cooled down enough to where it was transparent to radiation, and that effect stopped. And so if we look at this, what physicists call a power spectrum of the anisotropy in the cosmic microwave background, maybe this gets a little bit technical and a little bit abstract, and trust me, it's a little bit abstract for physicists too, but we still think this is pretty solid evidence, and we can determine by the spacing of these peaks and by the amplitude of the peaks. There's a lot of information in this graph, and we can extract from it how much dark energy there is pushing the inflation, how much dark matter there is pulling the gravity, and you can ask me about dark matter if you like, and how much baryonic matter there is that makes up you and me and everything else in the universe. And so we can, you know, it's just one line, but it's produced from this very detailed information of the cosmic microwave background in all different directions. And so, although it looks like it might be easy to write down a model that explains one line, it's really a little bit more than just that one line. And so we have still really good evidence that there was this period of hyper fast inflation in the very, very early universe for just a teeny tiny fraction of a second. but the universe blew up by such a large, immense amount that what's now the visible universe is actually just a tiny, tiny part of what we think the whole universe is. So if you've been feeling tiny earlier on in this talk, this is the part where you should really start to feel tiny. Not just is there a lot of stuff that's like way out there, and we are just, you know, one planet around one star in one spiral arm of one Milky Way galaxy, and that's just one galaxy out of, you know, several hundred billion galaxies in the visible universe. But the visible universe is really only a tiny, tiny fraction of the entire universe if this theory of inflation is correct. And I really do think that is pretty solid too. Not as solid as the story after 380,000 years from the Big Bang, but still pretty solid. And so I didn't put a number to it, but the fraction of the universe we can see, although it's you know, some you know, immense distance to the oldest stars where the light has left at the, you know, right after the Big Bang to travel all the way to us to reach us now. That's still a large space, but it's not even a percent, not even a, you know, billions of a percent. There's like many, many more zeros. The entire universe is vastly larger than the visible part of our universe. Okay, all right. So that's inflation in a way too short of a story. I know I'm already at an hour and 15 minutes, but any burning questions about this? Yeah, Ellen.
So you're saying the universe is flat, but we are, well, basically flat.
Yeah.
But we live in a three-dimensional world. So is the universe flat but thick, and if so, how far?
Right, no, by flat, flat doesn't mean two-dimensional. Flat means, flat in this usage of the word is a statement about the curvature of the universe. We said before Einstein in classical physics, the three directions in space are perpendicular to one another, and that's all there is to it. Now with Einstein we say, well, but if I put matter into space, matter curves space so that then some other object kind of follows what locally looks like a straight trajectory, but it bends, right? So locally we have curvature of space-time. And that's really pretty well understood and also experimentally verified through gravitational lensing and through all kinds of things, observing Mercury and observing you know, solar eclipses of the sun and so on. But averaging over such small things as stars and galaxies, what does the universe at a much larger scale look like? Well, it could still kind of have this curvature to it, or on a very, very large scale, although there are potholes in the road, although if you get close to a star, you may be deflected a little bit this way or a little bit that way. If you keep going, you are going in a straight line, or are you curving to one side or the other? Well, that's what flat means. So on a very large scale, it appears like it's still like these perpendicular axes. Maybe I didn't explain that well. So thanks for asking that question. It has nothing to do with like flat as in two-dimensional. So that's, yeah. And again, that would come about even if you have something that isn't flat, where so the universe is three-dimensional, but we can't envision three dimensions, and then distortions would be in a fourth dimension, which we have trouble with. So let's pretend the universe was two-dimensional. Okay, it could be like the curvature of an apple or the curvature of Earth, or it could be curved the other way around. It probably isn't flat, right? It's very unlikely that it would be flat. But if I start with something like an apple even, with very high curvature, and then I blow it up to immense size, much, much larger than the Earth, where by the time I make the apple the size of the Earth, I don't need to be an ant, I can be a person, and it looks flat to me right now, right? And if I make it not the size of Earth, but the size of the solar system, well, now it really looks flat to any measurement uncertainty, right? So, but again, this surface of a sphere is reducing the dimensionality of the problem just so we can envision it. The true universe is three-dimensional, of course. All right. Well, if you have a tiny bit more patience, let's get to the totally speculative part that, however, I think is right. This is going back to Lindy, who is now at Stanford, and other physicists. So what really caused the Big Bang, or how did this start? So we know quantum fluctuations exist. So what's a quantum fluctuation? It think about empty space. Is empty space truly empty? What does it mean? A vacuum. You hook up a vacuum pump, you start sucking air out, you have no air left in there, no atoms, just empty space. Is it truly empty? Well, it turns out not really. There is something called vacuum polarization. A very dear principle in physics that holds in all of science is conservation of energy. You really only convert energy from one form to another, you can't create it. But there's one exception to this. You can, even in a vacuum, pop into existence a particle and an antiparticle, as long as they annihilate again into nothing just a moment later. So that's compatible with the Heisenberg uncertainty principle. So you can violate energy conservation as long as you balance your energy checkbook before time is up, right? Before somebody looks too carefully. So the vacuum isn't truly empty. There is vacuum polarization is what we call this, these particle-antiparticle pairs popping into existence and vanishing again. And as fantastic as it sounds, we know this is true because we need to take this effect into account to model subatomic particles. So if I have, for example, an electron, it would have some amount of charge, but these particle-antiparticle pairs of charged particles come into existence and they orient during their tiny amount of lifetime and they change the behavior of the naked electron. We call it the dressed electron, dressed in these virtual particle-antiparticle pairs. So we know quantum fluctuations are real and we understand it based on Heisenberg's uncertainty principle. And so, you know, we know that happens. Well, space itself could also just pop into existence and vanish a moment later, okay? We think that actually should happen, that, you know, right here, right now, it could have happened. We wouldn't have seen it. We would never be the wiser. There would have been some tiny amount of space popping into existence and vanishing again a tiny moment later. Okay, that may sound crazy, but that could be going on, and we think, well, I think this is speculative, and I don't think all physicists agree, but to me this makes sense. So we could have these bubbles of space-time popping into existence and vanishing again, But once in a while, the initial conditions in this bubble of space-time are such that inflation starts, and even though it should vanish a moment later, by that time it may have expanded into such a large space that it can't vanish again. So cosmic inflation blows up the space in this huge, unimaginable, rapid rate. And then that false vacuum that drives inflation decays into the lower energy state of the vacuum we have now, and inflation stops, and the universe evolves in what we observe now. And so there may be many bubbles of space-time where inflation kicked in, but the conditions were different from the laws of physics we experience. So if this is true, if this is how our own universe started, then there should also be many universes that are totally boring, where there's no particles that can bind to each other. But they probably exist. We just will never really know about them firsthand. But we hit the cosmic jackpot, our own bubble, not just ended up in or started in such a state that inflation kicked in and kept us from vanishing a moment later. But on top of that, the Higgs field, the parameters of physics were such that interesting stuff could happen, and we are here tonight discussing where we came from. So anyway, so in other words, I think it's really just a chance of random quantum fluctuations, and I think our universe, as vast and as it is, and as little of it as we can see, is only one of many, infinitely many, a large number of infinitely many. There are different kinds of infinity, and so there are many universes out there, and ours is only one of many, and of the one we are in, we can see only a tiny part, and of what we can see, we can explore only an even much tinier part. We are really trapped on the surface of this tiny marble, so let's take care of it. All right, I'm open for more questions, but I've talked much longer than I thought I would, so yeah, Annie. Oh no, they aren't all boring. Oh yeah. Oh yeah, definitely. There are other planets with trees. What I've just said is that there are infinitely many universes, and each one is, if not infinite, at least extremely very large. And so there are countless planets like ours. And in fact, who was it? Anyway, one of my colleagues calculated, even before you get into these bubble universes everywhere, in our own universe, beyond, maybe not inside the visible part of our universe, but somewhere in that inflated, huge universe, statistically speaking, there's probably another first UU church just like ours, where people sit just like this, having the same discussion, talking about that other first UU church, and so on. And there is one where it's just like this, but the chairs are green. And there's one where it's just like this, but we didn't have the nice snacks everybody brought. And there's, and so on. And there's one where we have an ear in the front and two noses on the side, and whatever you want to make up, right? So each of these many things I just mentioned is exceedingly unlikely. But if you have that many chances to roll your dice, also most of the time you don't hit jackpot, once in a while you do, and we are by no means unique. Right. Kent, yeah.
Well, as flatlanders living in Kansas, it's been empirically shown by science that Kansas is flatter than
nice to know and enlightened that we are indeed mirroring the
Is it
inflation.
over? Ask some questions.
All right. Kent is saying the universe may be flat, but Kansas is flatter.
My question is on elasticity. When there was the Big Bang, was it like a lot of little ping pong balls on mouse traps? Or was it just a huge, big one shockwave? Or were there a lot of little tiny shockwaves?
Right.
Giving us elasticity.
So how did the Big Bang really happen? Was it just one thing, or was it like many ping pong balls on mouse traps, and one starting pushed the other ones, and then the thing blew up? Well, again, this is somewhat speculative, this last part. Also, I really think everything points to it, but some of this we just can't really observe. It's just beyond observation, right? But I think it's reasonable speculation, and if this is at all true, then it would be one event, right? One quantum fluctuation that then blows up. So, yeah. All right.
Okay.
Thank you.
Well, thank you, Holger. That was certainly mind-blowing. So we'll all have to think about that and read up on it some more. Well, thank you all for coming tonight. Next week, we will meet on the last Saturday of February. The topic has not quite been decided yet, but we'll keep you informed. So thank you all for coming, and we'll see you next month. That really was amazing.
Okay, yeah.
Very good.
Glad it worked out. All right, I hope everybody on Zoom had a chance to ask your questions. I didn't pay close attention to the chat. Oh, dynamic tension imbalance affecting Zoom. Oh, I hope the recording came out nice. Well, all right. Well, see you all next time, and thanks for joining.
Thanks, Holger.